The new device is called a bridge. A bridge is a small switch. You can understand it as is a data link layer product. Works on the second floor. The bridge has two interfaces. For the bridge, different interfaces are different collision domains. There will be no data conflict between the two interfaces. Let me give an example to explain the differences between bridge-based networking and hubs. For example, these two are bridge interfaces. In the meantime, they can send and receive data. Non-interference between the two. We can do this kind of work through the bridge. But the bridge itself has its own common problems. It also has only two interfaces. So the network is like this. A bridge in the middle. Connect two hubs next to a bridge. Then go to connect multiple terminal PCs. We can do it this way. To isolate the conflict domain on a smaller scale, you will find, because this is the hub, so this is a collision domain. But since this is a bridge interface, so actually, collision domains are only so big. Probably originally 6 PC conflicts. But now you turn 6 PCs into 3 PCs conflicting. One of its problems is that it has only 2 interfaces. So the number of interfaces is not enough. Then the switch appears. A bridge works like a switch. It differs from the switch in that there are more switch interfaces than. We'll talk about how switches work in a moment. The latest products are now available. That is the switch we are using now. Suppose now this is a switch. What can a switch do? First of all, it has many interfaces. I can now connect other devices to this switch. I mark these PCs. 1, 2, 3, 4. 4 devices. Let's say this is the 4 interfaces of the switch. 4 switches. How does it work now? First of all, the switch is also a product of the data link layer. Works at the data link layer. There is a very core parameter in it, called MAC address. The switch can record the MAC address of the terminal, and can generate a table on itself, called MAC address table. What is stored in this table? For example, now interface 1 of the switch corresponds to a PC1 below. Suppose the MAC address of PC1 is a. It will generate such a correspondence. Let's say this is interface 2, interface 3, and interface 4. It is possible to store such information locally, followed by BCD. Their MAC addresses are ABCD. A table like this will be generated on the switch. Since it has a table like this, it can complete a precise forwarding of data. If now PC3 wants to visit PC2, the MAC address of PC2 is B. Then it's making a data request. Do you still remember the ARP we learned before? We can request to the other party's MAC through ARP. Complete data encapsulation. If PC3 now has the MAC address of PC2, it sends a data to the switch. The switch sees that its destination MAC is going to be. The switch will query the local MAC address table. It is found that B corresponds to its interface 2. Send data out from interface 2. Then this data came to PC2 alone. Then this data is for PC1 and PC4. They won't accept. The switch can complete unicast communication. And the switch is a full duplex device. The interface of the switch can isolate the collision domain. All devices can send at the same time. And receiving data is not affected. So in fact, you can understand the switch as combination of bridge and hub. A hub is multiple interfaces. There is also a MAC address table in the bridge. Works the same as a switch. It's just that there are few interfaces. It is an advanced hub plus a bridge equal to a switch. All in one. In the end, it became the equipment we use now. Same. Within each company. In fact, they are all similar network structures. If you want one company to communicate with another company, it is impossible for all devices to be connected to the switch, including that we are now connected all over the world. It is impossible to network through switches. That's why we have such routers that are farther away and based on route forwarding. Eventually connect. This is the development of the web. I just want to tell you how the switch came from. Then we will start to formally talk about the content of the course. Today we talk about the principle of the switch. Here is a word. Ethernet devices including hubs and switches. These are the two most typical devices. Let's do a brief review. We just talked about hubs. For devices such as hubs, everyone must first be clear. Under what circumstances should we use such a device? I give an example. There is a PC down there. Multiple PCs now. Suppose a company. The number will definitely increase. Because the number of employees will increase. Everyone needs to communicate with each other. Everyone is on the same network segment. If you want to connect multiple devices. Middleware. So the first hub appeared. Connect multiple devices. The hub was the first of its kind. We use this device. Start connecting. After connecting, we need to know what the hub is based on for data forwarding. I just told everyone. It will perform flooding when it receives the data. But why flooding? How did you know? The data forwarding of the hub depends entirely on its current interface card. Under this interface, you can feel the voltage swing value under the interface. As long as there is data going through under the interface on this line, I feel that the data is coming now. Then the hub will receive and carry out flooding. Bridge is a name. It is a switch with only two interfaces. The processing action of the hub for data is flooding. Flooding means that the data ports other than this receive port copy all and send a copy. Here's how it works. So when the hub forwards, no matter what the data, it doesn't care where it goes. As long as the data comes, it will flood out. So actually, it cannot be called a network device. It is just a product of the physical layer. Because it has no CPU. It does not need to calculate. This is how it forwards. And let me emphasize one more point. We also said, if the data sent by PC1 is now, send it to PC2 here. It cannot be sent out at the same time. Data conflict. Therefore, the work efficiency of the hub will be relatively low. The concept of conflict domains we talked about before. We won't talk today. Today we mainly talk about switches. The abbreviation is usually SW. Switches work differently than hubs. Based on physical hardware. Everyone must first remember. For switches, each interface of a switch is a collision domain. Different interfaces are different collision domains. Then it means collision domains are actually small at the same time. There is only one line like this. So now receiving and sending data has no effect. PC1 sends data. PC2 can also send. For switch ports, you don't need to understand why it is different from the interface of the hub. This is an improvement based on physical hardware. That's what's on the hardware level. We only need to know its logical concept. And the switch's interface has a behavior. Self-negotiation behavior. Its interface can realize the negotiation of working mode. For example, the switch is connected to a hub. The hub interface is a half-duplex mode. The switch is in full duplex mode. Switches can be compatible to small. It can also be turned into a half-duplex mode. This switch is connected to a switch. The peer interface rate is relatively small. Its interface rate is relatively high. It can accommodate the other. Negotiate to a rate consistent with it. Backward compatibility. Therefore, the interface of the switch can be negotiated automatically. Each interface of the switch is independent. Then please pay attention. Once each interface is independently, it means that the data of one interface of the switch will no longer be perceived by other interfaces. So how does it work? How to forward data? We just mentioned the MAC address table. For switches. Actually, it's like a brain. This brain is the MAC address table I just mentioned. I'm going to make a logo for the PC. This is PC1. The MAC address of PC1 is AA. This is PC2. The MAC address of PC2 is BB. This is PC3. The MAC address of PC3 is CC. This is PC4. The MAC address of PC4 is DD. Let's simulate data sending now. Suppose PC1 wants to send data to PC2. Then they have to complete an encapsulation of the source MAC and the destination MAC. We talked about. There are two encapsulation methods at the data link layer. One is called E2. One is called 802.3. What we use most now is the E2 package. Now the data link layer is going to be encapsulated. The encapsulation is the Ethernet 2 standard. It has a parameter in it called SMAC and DMAC. Source MAC and destination MAC. Now PC1 is going to visit PC2. Source MAC is AA. The target MAC is BB. Then if such a data is generated, prove that they have made an ARP request. Already got PC2 MAC. This data wants to be sent to the switch like this. Then let it help perform the forwarding.